Hello everyone, I am presenting our recent work, a robust volumetric transformer for accurate 3D tumor segmentation. Inspired by the recent strong empirical results of the transformer-based models in computer vision for tasks such as classification, recognition, their good generalization and robustness characteristics, and their flexibility to model long-range interactions, in this work, we propose a transformer model for multimodal brain tumor segmentation tasks. Earlier efforts to develop transformer-based segmentation models for 3D medical scans have been shown to outperform state-of-the-art CNN counterparts. However, these methods divide 3D volumes into 2D slices and process 2D slices as inputs. Because of that, considerable and potentially critical volumetric information, essential to encapsulating inter-slice dependencies, is lost. While some of the recent hybrid approaches use convolutional blocks and transformer layers to keep the 3D volumetric data intact, designing a purely transformer-based architecture that can keep the volumetric data intact at the input is relatively unexplored in the literature. Therefore, our work takes the first step in this direction and proposes a model that achieves better segmentation performance and demonstrates better robustness against data artifacts. Our main contributions are: we reformulate volumetric tumor segmentation from a sequence-to-sequence perspective and propose a UNet-shaped volumetric transformer for multimodal medical image segmentation. We design an encoder block with two consecutive self-attention layers to jointly capture local and global contextual cues and a decoder block that enables parallel, shifted, window-based self and cross-attention. To further enhance our features in the decoding, we propose a convex combination approach along with Fourier positional encoding. Incorporating our proposed design choices, we substantially limit the model parameters while maintaining lower flops than existing approaches. We conduct extensive evaluations and show that our design achieves state-of-the-art volumetric segmentation results on the medical segmentation decathlon brain tumor segmentation task, along with enhanced robustness to data artifacts. This is the proposed network architecture. During encoding, we introduce a volumetric transformer block with a window-based multi-head self-attention approach. Figure B shows how volumetric window-based self-attention is calculated. Assume this is the MRI volume. During the first step of the VT encoder, it creates volumetric windows like this and does self-attention. In the second step, we shift this volumetric window with some stride, creating more volumetric windows like in this figure. For each window then, self-attention is calculated. Using this shifted window approach, we can extract long-range dependencies of this medical volume. For bottleneck layer, we use the VT encoder block. Compared to the encoder block, the decoder block structure is somewhat complex. Here we introduce a knowledge transfer mechanism by transferring K and V weight matrices from encoder to decoder in addition to standard skip connections. During decoding, we parallelly compute self-attention and cross-attention to improve feature learning. We introduce a fusion block that combines both attention outputs in a convex manner and uses a sinusoidal version of Fourier feature positional encoding to improve segmentation accuracy further. This figure shows qualitative segmentation results with tumor subregions ED, ET, and NET/NCR on the test samples of previously unseen patient data. We can observe that our model can accurately segment the structure and delineate the tumor's boundaries. This table shows a quantitative comparison of segmentation results. We use two evaluation matrices, dice similarity coefficient, and Hausdorff distance. It can be seen that our approach consistently achieves the best overall performance with dice score. We believe that capturing long-range dependencies across adjacent slices plays a vital role in our model's performance. Also, we conducted another experiment to evaluate the model's robustness to data artifacts. We added motion, ghost, and spike artifacts to patient MR images before feeding those to the VT-UNet model. The results suggest that our approach performs more reliably in the presence of these artifacts. Our results show that the proposed model achieves consistent improvements over existing state-of-the-art methods in volumetric segmentation. We believe our work can assist in better clinical diagnosis and treatment planning.